All right, so welcome to week 3. We are going to be going over backpropagation, training a neural network in implementation, and we're going to go over the deep learning framework PyTorch. All right, so we don't have much time to cover it because we were a little late last lecture, so go through this a little bit quickly. So, as you may know, we went over this last time. We have parameters versus hyperparameters. The parameters are anything you learn during your training time, so your weights and biases in your neural network. And hyperparameters are anything that you set manually, so learning rate, batch size, and you'll learn more hyperparameters as you create more complex neural networks. So we're going to revisit the cost function. So basically it's how off your model is. It's your error. And so the cost function is a sum of the error on all of your training examples. So it's a sum of losses, as you can see. And for I equals 1 all the way to m through all your training examples. And the general form of writing it is this, j of theta. And theta denotes your parameters. So that could be your weights and biases, essentially. So our goal is to learn what are the correct weights so that we can fit this kind of line or a curve to our data. And to do that, we just measure the error and backpropagate that error through our network and change our weights in such a way that will reduce the error. So how do we actually do that? Well, a more specific answer is that you calculate the derivative with respect to the cost function, and you get a numerical value of change for each individual weight, and you change each weight by a small amount. So the derivative is essentially the slope, and it tells us where to go in the direction of the lowest error. So here's a more graphical visualization. So you can see that there's two local minima where the arrows are pointing. That's where the model has the lowest errors for parameter 0 and parameter 1. So you can tune your parameters in such a way that you want the cost function, j of theta 0, theta 1, to go towards the minima. So when your cost is at the minima, that means that you find the best model, because in that case, you have the lowest error. So to do gradient descent, basically at each step, we're computing what direction do these parameters need to change. And the change is equivalent to the gradient, or the derivative. So, for example, for parameter 1 or 0, we compute the slope at the single point where we got the value for the cost function. And we say, well, we want to move in this direction because the slope is going this way. And so that's how we compute that term right there, which is equal to the slope. And then the same goes for this one. We have the slope pointing in this direction. So that's the derivative, and the derivative equals the slope. And so also, this is also called the partial derivative because we're taking the cost function with respect to a single parameter. And so if you learn this in Calc 3, and I've sent out reading notes of a list of terms you should know. Partial derivatives in there, gradients in there. So if you're still confused, just look back at those and Google the terms. Okay, so here's the gradient descent algorithm. It's a very simplified version, but basically you have all of these learnable parameters. The parameters you need to tune so that your model changes in behavior. So for each parameter, this is parameter j, this could just be one entry in a list of a bunch of vectors or matrices. And so basically we compute the derivative, so d theta j of the cost function j, and that will tell us what direction is the error. And once we know what direction we want to go, we adjust our parameter by a small scalar times this derivative. So basically, the intuition is that on a gradient, you're taking a small step towards the local minima. Is there any questions on this so far? Okay. So now we're going to move on to doing it for neural networks. So when you're computing the cost function, you need to go over all of the examples, and before that you go for each iteration because you have to iteratively update your weights. So at the first iteration, you would go and for one example compute the loss for that, second example compute the loss, third, all the way up till you completed the loss for all of your examples, and then you sum them to get the cost. And so now with the cost function, we can compute the derivatives. So basically, we're taking all of our weights and biases and we're updating them. So any questions here? We'll go into more of the notations after this. But essentially, we have W1, which is the weights for the first layer, W2 for the weights for the second layer, and then similar for the biases. Okay. So to compute that, we use the chain rule. And basically, the chain rule is calculating the derivative of nested functions. So as you can see here, we want to take the derivative of f of g of x, then we take the derivative of f, and then take the derivative of g. So as you can see here, if you want to calculate in a neural network what is the derivative of j with respect to w2, then what we have to do is we have to expand all these terms. And as you can see, we can cancel these out by multiplying them. And so you get the same thing, dj, dw. And then if we want to calculate the weight matrix for something that is more deeper in the network, we have a more longer multiplication there. So we'll go over this more, but that's the basic intuition of the chain rule is like you basically expand what is the gradient or what is the derivative, and then multiply it by each term. So here's a more simple example. Say we have this function here, and it's x plus y times z. And we have this intermediate term, q equals x plus y, and then f is q times z. So as you can see, f would be equal to that top one. And so this is what is called a computational graph. We use this a lot in deep learning just to show how our network flows. And usually it's modeled by layers, but in this case, we'll model every single operation. So as you can see, we model q, which is over there, which is the sum of x and y, and then we have a multiplication operator to get f, so z times q. All right. So now let's say we input these values for x, y, and z. So we'll put those there. And then through our forward pass, basically we say what is the value of q? Well, it's just the sum of those, which is 3. And then what is f? Well, it's the multiplication of 3 and -4, which is -12. Okay, so now what we want to find is what is the derivative of f with respect to x. So what we do is we decompose them into their two parts. So f with respect to q, q with respect to x. And then you can see these operators would be applied on this. So what is the answer? So q with respect to x is 1 because when we take the derivative of this term, this y turns into a constant, and basically the derivative of that is 0. And then this with respect to x is 1. And similarly, we do that for the df dq, and we get z, because in this case, z is a constant, and so that it's like a constant multiplied by q, and so we get z back. All right, so if we want to finally get the value for that, we just say, what's the value for this, which is 1, or z, and then the value for this is 1, so we multiply that. We get, substitute for z, we get -4, and we get -4. So what does it look like in the computation graph? Well, if we take the derivative of f with respect to f, that's 1. If we want f with respect to q, now it's different because we are basically taking, so we have this term here, and then z is equal to -4. And then if we want f with respect to x, it's also -4 because we have computed this. So basically, as you can see, it's like we multiply backwards, and that concept of multiplying backwards also applies to neural networks. Okay, so basically in a neural network, you would just do the same thing. This is how you would multiply backwards with some specific functions. So if in the case you wanted to compute like this W1, you basically have to go apply the chain rule through all of these equations, and then take the derivative for each of them with respect to this first value here. And we'll go over that after, but that's the intuition. Okay. So next up, we're gonna go and speed things up with linear algebra. And this involves using vectors and matrices to model our equations. But why do we want to do that? Well, it turns out that in GPUs, we can take advantage of these multiplications because basically it's very parallelizable. And what that means is in a GPU, you have tons of GPU cores, and each core can do like a small operation. And so in a matrix, you're doing basically the same thing, same operation, which is pretty parallelizable. And so this is used heavily in like different libraries like NumPy and TensorFlow. And there's also like a efficient way to do those operations. So now, if this is just a brief recap of vectors and matrices, a vector can have a direction and magnitude, but usually we model our vectors at this. So this is like a feature vector. Our example as before. These individual values could have some meaning to it. Or we could have a matrix, and this would be our weight matrix that we'll go over. And each individual weight has a different effect on what is important in our features. And so here's some matrix operations. And so a dot product is basically we take two vectors, multiply them, and then add them. That's basically a weighted sum. And we see that in our operations with the neural network as well. Matrix vector multiplication, and then matrix multiplication. I'm not going to go over this because we're out of time, but so here is our equation that we had before. Basically, this is like from one neuron, and we take the inputs and multiply it by a weight, add a bias, and then we get our affine value, which is z. And what we can do is we can take that and put it into a dot product. So as you can see, if you take the multiplication, basically this multiplies by this, and etc. They multiply by a row, and we add a bias, and then that turns out to be equivalent to the top one. And so we simplify that and just call it WLT AL minus 1 plus B. And then we can do the same thing. Because Z is a scalar, we're just applying a function GL on that scalar, and it should give us one value. Any confusion on this? Yep.
You said chopper is the dot product.
Yeah, this is equivalent to the dot product because this is the transpose of this vector, and then when you do a matrix multiplication, each term is multiplied by a corresponding one. Yeah, it's just like different notation. All right, so here is everything before. We're just going to condense that. And here's an example that we had previously. We take those numbers, put it in a vector, and then there's a bias, and we get our value. And if we put a ReLU, it's just the same value. So now we're going to do vectorizing across all activations. So this is the equation for the first activation. And then we have the equation for the second, and the third, and the fourth. So basically, it's the same thing we had in vector notation, and we are just repeating that but we don't want to repeat it because we want to vectorize it now. So instead, what we do is we take everything and vectorize it. So as you can see, this is in our final vector here, and that's also equivalent to this, which we'll simplify down to. And so for each thing, we just take it, and we're going to put it here. And then we take this, x, and then put it here. And then take b, etc. And so by doing this, we can just see what happens when we multiply this out. So if we multiply x out, this x transposes, or comes around and then multiplies by each entry in here. So that turns out to be the same thing as this. And then once we add a bias, then we add the bias in this. So it turns out to be a matrix, or a vector form, which ends up at the end.
What is the one on the top right corner?
This one? So this is what you do after you get Z. So this is the step right before you get the activation. So for each Z1, for example, you would put it through G and then get A1. And then Z2 gets A2. So this is just one thing, but we can also vectorize that out as well. And then that looks like this. So this is, now we have a weight matrix because when we took this before, we expanded the vector on its side, and then now we have a matrix because it's the number of previous activations by the number of activations at this layer. So this would be, the height would be 4 in this case, and then the width would be 3 because there's 3 input features. And as you can see, that's why we have x1, x2, x3 there. And so that's equivalent to this weight matrix, WL. Any questions? Yeah?
It's the first one is cross product, it's not dot product.
Yeah. So this is matrix multiplication. Yeah. Okay, so once you do that, you would basically go layer-wise for each example, and you would compute that. So basically, that's forward propagation in a nutshell. So you compute the first z, then you compute the activation, that's this row here, or column there, and then you compute the second z and the second activation, which is the final output. And that's for a single example. So we didn't think about multiple examples yet. So we want to go and vectorize across multiple examples. And basically, you can think about it like this. We're taking a neural network for one example and stacking it on top of each other. So for this example would be there, but you could have different values under it. So if you think about it more in 3 dimensions, it's more intuitive that way. So here is like the standard algorithm. You would forward propagate for one example, for the second example, etc., until you get all of the examples and then compute the loss. Right? And so what we can do is we can frame this in a more visual way. As you can see, this is like how many entries there are for the first layer. So there's 3 inputs and then 4 outputs. Okay, and then basically to vectorize across all of the examples, we essentially stack them. So as you can see, like each entry would be the same for W, but each entry within A would be different, because A has values for each different example, but we are replicating W across all dimensions, so it's basically a copy of itself. So it is a weight matrix still that's copied over across multiple examples. And that same thing goes for B as well. So if we want to actually calculate it, so we take this whole thing, A, and we multiply it by the first row, and we get the first value. And we go for the second one, the third one, and the fourth one. So that's how it corresponds to the weights and the output. And so we take that and we put it back there. Now we have this addition, and this is just element-wise, so each part adds to the other part. And we get this result. And as you can see, it's the same dimensions as Z. All right, so now we have our activation function. Basically, we just have a giant function that does an element-wise operation on all of the values. So it can be anything, but it's just element-wise. So there's nothing special going on, really. But we can still parallelize that because it's a simple operation. So we get that, and we get the result. So basically, to vectorize gradient descent, instead of forward propagation, going backwards and computing gradients, we're basically doing the same thing. But instead, we're just doing a matrix. We're computing the derivative of matrix. And then we use that matrix to update the weight matrix. So if you can think about it, you have a derivative, but you have multiple derivatives that are in like a matrix, and we're just taking that and pushing it backwards. Any questions so far? Yeah?
Did we go over activation function before, or
Yeah.
can recap it?
So activation function is basically, all right, hold on. Here, okay. Yeah, so it's like, this is like an activation function. It's just a function that applies, you just plug in the value here and then it spits out something that usually squashes it. Yep.
I'm kind of confused by the back propagation by the matrix
Mhm.
derivative.
Yeah.
Can you re-explain that just a little bit?
Okay. So here, I think there's slides here that we'll go over. That's more better to explain it. So basically, at each step, we want to compute the derivative through the chain rule, right? So we have a computation graph that we're stepping forward through to compute the forward propagation, and then to do the back propagation, we basically take the derivative at the first layer for every single value in like the first weight matrix, right? So for every value, you take the derivative. In our example that we had back in here, we're doing these operations, but just doing them simultaneously. So it's not any different. It's just like the way that you notate that in a matrix form is a little bit different. But essentially, you're doing the same calculations.
Is it like a transformation matrix?
Yeah, so it's, well, to fully understand it, you have to know a little bit of matrix calculus, and that's basically how you take derivatives of matrices.
Okay.
And there's something called a Jacobian matrix, but we're not going to go into that. So,
Okay.
yeah, if you're confused on that, search matrix calculus for deep learning, and there's a lot of resources for that. Okay, so running out of time, but we're almost done for the first half. So back to here. So this is the equation we had before, but we take the derivative for each part and then update it in a matrix fashion. And then here are the actual derivatives that we would use for a two-layer network. So this dz, like for example, that means just the derivative of the cost function with respect to z. So that's this shorthand notation for all of these. And all of this stuff is already pre-computed. Usually if you're doing something in a deep learning framework, they'll all do this for you. And so that's why we don't really cover it in depth, is because we have all these powerful tools that compute these complex gradients for you. And those are done through the chain rule, essentially. So you can break down all of the computations very small into very small chain rule operations. And so that's how you get that, the derivatives. Yep.
And every layer is essentially the same except maybe the inputs of the A's, weights and everything, they're all...
Yeah, so essentially the same formula repeats for each layer, but you would just have like different inputs and outputs.
Mm-hmm.
Yep. So here's some derivatives for the activation functions. As you can see, here's like sigmoid, tanh, and ReLU. For the sigmoid, the reason why we don't use it anymore inside of our neural network is because we have these places where the slope is essentially 0. So when you compute the derivative is 0. And that means when you do backpropagation and your update for your gradients, then you're multiplying by 0 in your chain rule, and then you basically have no update for your weights. And the same actually goes for tanh as well. We have these places where the gradient is 0. And so that's why we use ReLU typically in our networks, is because when you're on the positive slope, it's always a gradient of 1. And so we don't have this problem of, what do you call it? the vanishing gradient problem. So basically, when you have a number that is less than 1, it's like 0.5, and you multiply that to a very high power, then the limit of that is equal to 0. And so when you have a 0 gradient, then you don't learn anything. Yep?
Aren't there trade-offs to switching like a smooth curve to something like that? Is there any?
There's not many trade-offs. In implementation, it's actually pretty simple because, as you can see, like the formula is just like fish lists, and here you can easily implement that in like computer, like low-level code. And the higher ones are a little bit more complicated. It just makes like a small performance hit, not really that much. All right, 5 more minutes, and then we'll take a break. But now we're going to move on to deep neural networks. So basically, we're going to take this and abstract it. So a layer operation is basically going to be, we have this A vector, and we compute a function on top of the previous layer. So the previous layer is AL, or AL minus 1 in that case. So in forward propagation, basically we're doing a ton of layer operations until we get the output. And so this would be like the explicit notation, but instead we're just going to make it very simple and just call it some function on top of a vector, or on top of this matrix, because the depth of this matrix or tensor is the number of examples, and then the height is the number of activations for that layer. All right. Any questions? All right. So what is a deep neural network? It's basically more layers, and that's it. So there's not really much to explain other than that. And we use more layers because basically as we add more layers, it can learn more complex functions. So yeah, and so like in the lower example, the lower layers would like detect small lower level features of the image, like edges, different kinds of shapes, and then the higher ones would detect like parts of the face, and then like the last one would have like a whole face. And so to do like backpropagation on a deep neural network, basically just compute the values for these and then store them somewhere so that you can use those stored values to compute the derivative. And then to compute the derivative at some layer, you would just multiply all the gradients previously, and then that is used for some, it would be used for the update rule. And yeah, that's some of the matrix form of that. But here, like, if it's a deep L neural network, then you basically repeat this process a bunch of times until we get to the end. And so this is like another visualization of that. And so that's it. So basically, for a neural network, we just compute the forward propagation, compute the costs, backpropagate, and update the weights. So yeah. So you can get some pizza, and then after this, I'll take a 5-minute break and do our PyTorch demo, and we'll go over like the code that you need to implement for this. All right.
I'm going in like 45 minutes and going on to that. Okay. Rob and I are trying to for 45 minutes because I gotta like rewrite my diffie work. So it's like I gotta do it in the last one because I boxed for answers. He doesn't want you to box for answers.
I was like Oh, I told Jennifer I was gonna post it. So that's why I'm gonna contact with you. Okay, because you know I'm gonna promise today. I'll see you next week.
Yes, he has he wants
What?
to
All the slides are on.
make it
Okay, yeah, just like my own thoughts.
Okay.
I think so, yeah. I think he already has data. He wants me to validate. He will validate like this and that his data, and then he uses this model for other stuff.
For the next part, they're gonna start singing Google Slides. Yeah, so we're gonna get code on that.
Yeah. There's like no learning. It's just like a path, basically. If it fires in that right path, you don't get the certain So just how it works in the brain.
Hi, I actually have a question about the sigmoid function part. You said that it's because the gradient is like 0. So what if like you stretch the sigmoid function so that, and then you limit the range of x?
Right.
Is that possible?
You could do that, but the problem is then the network will learn larger weights.
I see. Okay.
So it would still face the same problem though.
I see. So is it in industry people usually use the value thing? Okay.
Always relevant.
Okay, cool. Thank you.
No problem.
I'm a little confused on where exactly are we taking the derivative of whenever we take all those derivatives? Because it seems like we just took the derivative of everything.
So, say you want to get like a specific entry in the matrix. I don't know which. Okay, maybe this slide.
So, I didn't notice. Say we have like, we want to use like, I just try a bunch of different
Yeah, you can add to get to certain behavior.
Then to get that value, it would just.
Because that's kind of, yeah, that's what you, so you kind of really, like,
So this would multiply. That's how you multiply
a
it.
certain firing.
But
Like a certain path.
if you want to know the
And every
specifics,
time you think of
Then
this is what you would do.
the same path.
So you would take that,
Yeah.
and you can see like
It reinforces that, and then so like
oh,
if that path fires off, then
so this is equivalent to that. So that's how you multiply. That's why it's
yeah. But then also the path.
Because it was like,
in that like
I get like taking the derivative to do gradient descent, but then like when you do that and then you update the weight, so you update like the values that you should have, right? Or no, you update the weights.
No, this is so that model with multiple.
Can I ask a question about
the weight percentage? What's the probability that this one?
Which one exactly?
It was keep going.
I don't know.
Oh yeah, it's farther up. Oh yeah, it's 50. This is kind of super punchy, but you're like, this is like simplified, right? They like fit on the page sheet. That was the joke.
Well, it was everything. Right? Like everything in the pictures and places.
Also, this is for Z. So that's just that one like
This is like
but yeah, like basically you just use this.
I think
So now it's
This would be like,
this would be like
no, so this would be one scalar, and then we use also so then this result turns into one value. So it's just one. So maybe it'll just
Is this forward propagation right now?
yeah.
Yeah, okay, so multiplying the values by the weights, and then by it, and then getting a value. Okay. And then
Yeah.
Then you get that one vector value. And that's
So like basically, I introduced some order and I started deciding this really weird.
So you take plug it into here.
I didn't really get it. Like, I was
and then that's the set.
after like
Right.
I was like, okay.
And then for to move on, we basically do the same thing, but it would make one weight for one.
Yeah. So it would just be like this one.
Is this what?
Yeah, just do one weight.
I kind of still like
Yeah, I think I was just getting confused when we were doing like forward and backward stuff.
I'm not
Z is defined by A is defined by. What's Z?
Z is that and just forward and then put it in.
yeah.
It's fine.
Okay. So Z is just one point.
That's it. That's what gets
So G is the active number of right? So
Yeah, for your major.
taking this and then first time
So why are you gonna let's see like what is
I mean, it was a reading again
we'll just take this factor and put it just because.
Oh, okay. I
She
didn't
is
know.
Yeah.
Or like since the social part, or you guys create.
One is the tricky aspiration function is kind of like
Not really, maybe because I can answer now.
aspiration procedures.
So X is the
Yeah, I think the semester, the first. And then double major.
Not in the night, buddy, not in the night.
Yeah.
Not in the way he's.
But I mean, if I have it in common, I'll take it.
Are you just talking about?
Like, see, it's in school.
So once you get now I get used to it.
Alright.
But I'm like,
Like when we're orientation. Or do you get that in another layer? Or
Oh my god.
So for A2, that would go to for the
No. It's not hard to remember. It's the difference between one and Z. It's not a transfer, so it's
Yeah, I mean, you're really
You're not really so much better here. You really will like be the light of our life.
Yeah, it's nice.
Alright, so you can find the materials here. We basically have a link to our GitHub. And in there you find the slides, you can find the IPython notebook. And that's the same as this Google Colab. So if you click on this link, you'll get to here. And this is just like what we'll be using for demonstrating purposes. So what Google Colab is basically it's a way to run your deep learning models on the cloud, on Google servers. Basically, it's if you heard of IPython notebooks or Jupyter notebooks, it's exactly the same thing, but you just have a server on Google's cloud. And so what you can do, you can also use GPUs on this for free. And to do that, you just do runtime, change runtime type, and click GPU. Also, if you want to run something but you don't want to make changes, you can do make it a playground mode. So this would open in playground here on the top, and then that'll create your own environment where you can run anything. So to start, you just make sure your runtime is set to GPU here. And you can also use a TPU if you know what that is. It's basically a tensor processing unit, and they're really good at doing matrix operations or tensor operations. And to start, you just click connect here, or you can use your runtime thing. All right, so we have our runtime connected, and yeah, so here are some stuff. It's basically what I said but repeated. And then here's another thing. So for classification, if you're gonna do a question,
What's the difference between a tensor and matrix?
I'll explain that a little bit. So here's binary classification. When you would use like a sigmoid, because sigmoid produces value between 0 and 1, a probability. So if it's 0, you say no. If it's 1, you say yes, basically. Or is an object within this image? Yes or no? And then a softmax instead gives us a probability for multiple different classes. So a class would be just like a label for what kind of object or is in the image, or it could just be some like label. So like you could say, what if this image is a cat or dog or monkey, and then it would give you a probability vector that sums to 1. So the total probability is 1, and that's a rule of probability. Okay. All right, so we're going to go over tensors. So basically we have a scalar, which is one value, vector, which is column values, matrix is a table of values. A tensor is now a matrix, but another dimension. So you can look at it this way. In Python, it's basically a list of lists. So a tensor is just like, you could think of it as like a 3D matrix or a 4D matrix, and it could have as many dimensions as you want. Usually we don't go up to like 4 dimensions when you're using like convolutional neural networks or something, but sometimes you might want to add like time, for example. Sometimes you want to add just how many examples you have, so that would be 5. Or RGB values, that's like 3 different things, so it could be many dimensions. So we just start off by importing our packages. You run that, and then if you get this thing, you just say run. Yeah, so let's go over, we'll create a tensor of 1. You just run that, and you get 1. If you want a vector, you can do that. We take any Python list or tuple and put it in tensor, and we get that. If we want a matrix, you can take a list of lists and plug it in, and that gives us a tensor. And then if we want another tensor, actual tensor, we can put in a list of lists, and then we get that. Let's see if I can clear all the... Do you know how to clear the outputs for Jupyter Notebook?
Reset all runtimes and do it.
Okay. It's not. In view? Collapse sections? No. Oh, clear all outputs. There you go. Okay, so let's run that again. All right, so if you're familiar with NumPy, it's basically like a linear algebra library for Python, but PyTorch is basically built similar to NumPy. So if you want like a random matrix that's 3 by 4 wide, then you can do that in NumPy like this, and we get an array. But if we want to do the same thing in PyTorch, then we just have torch.randn, and we will get the same dimensions, but a tensor instead. We can convert our tensor xt into our NumPy array, and if we do that, this is what it looks like. So as you can see, we have the same entries on the top and the bottom, but this is just a NumPy array that it outputted. And the same goes for our NumPy array. We can turn that into a tensor by using torch.asTensor. And we run that, and we get a tensor. And so if we want to get the fourth column here, we can just say we index this operator selects everything for our row values, and then this gets this gets the third column. So if we get that, you can see we can do that for NumPy and PyTorch, and they're both the same notation, and we can do the same thing in NumPy basically, and then get the same results. All right, so now we're gonna put the tensors on a GPU because we want to run this faster, or run operations faster. Here's just a simple stopwatch function I made. And then we're basically gonna generate 2 tensors that's this size, and then we're gonna do a matrix multiplication. This @ symbol is shorthand for a matrix multiply operator. And you can do also torch.multiply, I believe, to do the same thing. Or like torch.add would be the sum operator, etc. So if we run that and see how long it takes, and this is the notation for putting a tensor onto the GPU. It basically takes the tensor in memory and copies it right over to the GPU memory. So in RAM to GPU memory. And so if we run that, there you go. The second one was much faster. Yeah.
Also, just to reiterate, you want both variables to be mounted on the CUDA, otherwise it like breaks if you have like one on.
Yeah. So the reason why we put both tensors on the GPU is because if you just do an operation in between, then it'll break because it can't do that operation. And sometimes when you do deep learning, then you have to look out a lot for memory constraints. So, and also if these CUDA operations, putting them on the GPU takes a while, so you want to put everything on the GPU beforehand, before you run things, usually. So here's automatic differentiation, also known as AutoGrad. Basically, what I said before is like when you do deep learning, you don't actually compute your gradients yourself. The framework does that because it knows what your model structure is, and therefore it can guesstimate like not guesstimate, but like actually derive the formula to compute the gradients. So if we run this, we can create an x and then get y from x. And because you can see below, 3 times 2 plus 1 equals 7, and then we get this grad function thing. The reason why we get this is because we said requires grad equals true, and basically that means it stores like a computational graph, and then PyTorch will use that to compute any gradient that you want. So if we do y.backwards, that will essentially compute the gradient for everything in the computational graph, And then when you say y.grad, we'll show it that the derivative is 2, because we calculate dy dx, then 2 times x, then we get a derivative of 2 right there. So here is an example. So this is the example we had before and our computational graph. So I want to take like 2 minutes, if you can write your own code to find the derivative of x. So find df dx. And you can look at the code above to have an idea of what that means. So if you have a computer, you can pull that out, but I'll wait 2 minutes. Alright, I guess I'll go over the solution now. Sorry if you didn't have much time, but we're running out. But so anyways, here is like an example solution. You could do it many different ways. But this one, I believe, is the most concise, or you could do one step maybe. So basically we create 3 tensors for our inputs, x, y, and z, and we define their values. And we can actually put this term requires grad inside the tensor function call. And we just say q equals x plus y, and then f equals q times z. And then we do f dot backward to compute the gradient. And then we print the gradient here for x. And we get -4, as we expected. So we can do the same thing for tensors as well. So if we can make a tensor x and a weight tensor w, and we say they both require grad, or actually only w does. And here's a bias, and then we just do a linear regression right there. So we do that, we get a tensor of 9. And then we can compute a loss function. Say we actually wanted 5 as our actual value. And then we compute the loss, which is 4. And then say we want the derivative of w. We have this value. And then if we want to update the weights, we can do that. So w equals that. So we have the learning rate times our derivative. And then, as you can see, it changed in a small direction. And now, if we show the loss, our loss is 2.6 from 4, which decreased. So that way you can see how you do gradient descent. And so we have some more slides, or actually some more stuff here. We have neural networks and going over a more abstract way to do that. So if you have to leave, you can leave now, but I'll just be going over this for a few more minutes. And this is up on GitHub, so no worries if you don't need to. Okay. So we go back. So the cool thing about PyTorch is they have a lot of things online, like pre-trained models, data sets that you can easily download, and you can download it in one command, like that. So I'll get it and download it onto your device storage. And you can see here that shows how much it is. Yeah. There you go, we downloaded MNIST, which is a data set of handwritten digits. And so if you want to show what one looks like, here's a 5. Yeah. And so we can see what are the dimensions of our data set. And this is the training data. So we have 6,000 examples, 28 by 28 images, and they're black and white. And so we define our device to be CUDA. This just says that we want it to be our GPU. If we put CPU instead, it will run everything on the CPU. And then, so we, in this code here, basically design our network. So I have W1, B1, W2, B2. This is like the example we saw in our slides. So basically we initialize it by getting a random matrix by this size. So the first one would be an input of 784 by the layer 1 activations, which is 100. And then our layer 2 size is 10. And then we would get, because the reason why we want the layer 2 size of 10 is because there's 10 different classes, 0 to 9. And then we take that and put it on our device, which is CUDA, or our GPU. And we multiply each weight by a small term, 0.01, just to make sure it's like close to 0, so that we're not too far off when we initialize our weights from the actual value. Yep?
Why did you choose layer 1 size input to 100 and layer 2?
So those are hyperparameters, and there was no reason. I just decided 100.
Can you do like 200?
Yeah, you can do whatever you want. You can try it yourself, just on the code. Yeah. So, and then we say they all require grad. But you can also put this, I think you can put it in here. Just say requires grad equals 2. So we have some equations here that we'll use for our network, and that's just to make sure it passes through correctly. All right, so we'll run this, and then we'll define our functions, softmax, relu, and our model. So these are just these equations, but in code. PyTorch has a bunch of different predefined functions in F here, torch.neural-network.functional. So we use that for relu. And our model is this, which are the equations we saw before. Okay. So we'll define our loss function to be the cross-entropy loss function. This will require a lot of time to explain, so I don't really. You should probably just like watch a YouTube video on this, but yeah. And then we'll just import this to have our training loop. And our targets is basically like the label of the number. So 5 would be just like a handwritten 5. And then here's our training loop. So we define our learning rate. We define how many iterations. I'm just going to keep it 1 for now, otherwise it would run forever. And then we'll have our history. We have our X and Y. And we have M, which is our number of examples. And M would be 60,000. And then for each step in our training iterations, we just have a loss for that epoch. An epoch means, an epoch loss is basically loss over all of your examples. So you could have an epoch. So one epoch is basically once you go through every single example, but you could like do an update iteratively. Like you could do one update for one sample until you do go over your whole data, and that would be one epoch. And so we can do that for I iterations in our data set. So I run this, and we say predictions equals model, and we input x, and then we take our predictions and then our y value, and then we compute the cross-entropy loss. We take that loss and add it to our epoch loss. But then we do this loss app backwards to compute the gradient, and then we can update each of our weights here. And so this will finish in about 17 seconds. So it's going through every single example and then updating the weights by a small amount. All right, there you go. And then it's going to be only one example, so it's not going to plot anything. But so now we want to make it more abstract. So we can do this. So there's some cool libraries in here: neural network, optimizer, and our data. We have our data loader and our tensor data set. And basically, we can define our model very simply right here. So this is the same thing as what we did, but very simple. So neural network.linear creates a fully connected network, or for one layer, and then we can just define our input sizes. And then neural network.value would be our activation function for that layer. And then the second layer would be another linear layer. Well, and we have our dimensions from going from our previous layer 1 size to layer 2 size. And then that's the output. And then we take our outputs and put it in a softmax. And we say dimension equals 0 because for like PyTorch requires a lot of like concrete dimensions, so you know what exactly aligns with what, and those are like usually the source of error when you create your own models. So watch out for the dimensions. And then we just do model.CUDA just to make it on the GPU, pretty simple. And we say cross entropy loss equals neural network.cross entropy loss. So it's very simple. And then we say our learning rate equals that, and our optimizer is stochastic gradient descent. So that means just take an update every example. And then we say we're going to optimize these parameters of the model. So just do model.parameters. And then we want to say our learning rate equals just our learning rate. So it's very compact. It's kind of like Keras, essentially, if you've heard of that. So now we're going to create a new data set. And then we're going to just pass our data set into our data loader. So the reason why I did this is just to like flatten out the matrix form of the image into just one vector of features. And then put it into float because you get an error if you train something that's not a float. And then we have our targets, which is just our labels. And then we say our data loader, and we say our batch size equals 512. Batch size is basically how many examples do we compute a loss until we sum them and compute a cost. And using that cost, we do backpropagation. So basically, we're chunking our updates of the data set. Yeah.
Are those like the layers of the tensor?
Yeah, so that's like how deep it is, basically, in our example. And then we just like do a bunch of them sequentially, basically.
Why do you choose 512?
It's just another hyperparameter, so you gotta experiment around with that. We do have slides on this later, because there's a lot of different tricks to get your deep neural networks working really well. So we'll go over that in next workshop. So then, as you can see, our iteration loop is very simple, our training loop. And you can just run that. And notice that this is one epoch, so it's going way more faster. So we're doing 100 iterations on our data set, and that will take about a minute. And then we can run that, plot her history. And yeah, that's the end of this presentation. So if you need to go, that's it. You can stay for like 30 seconds to watch the results. But yeah. Yeah, question?
Why is that wrong? There's times
So it's actually, it's like basically a couple order of magnitudes faster. And the reason for that is like,
No, I mean like
huh?
steps that you're showing us now. How is it different from
Basically, we vectorized it a little bit and then took the stuff we had and put it into abstractions of PyTorch. So PyTorch is actually handling those updates for you instead.
Oh.
You can't edit it.
So this is like already well actually write code.
Mm-hmm. So this is what you would want actually. So the previous one is just like how do you represent everything explicitly, but this is more abstracted out and it's much better for speed. Oh, whoops. Oh, well, something gone wrong, but usually it just goes like a curve like that. Yeah. Not sure why, but
As long as if you don't know, then I'm just gonna push it.
can change our value.
I don't want to get hassles on the little details. No, I'm just gonna.
Yeah, so if you max out the RAM, it just crashes. But those are the resources allocated on that specific machine. Yeah. Google, most of the time,
I think like Google